In this video we're going over some M2 questions from the international paper of Friday 17th of June 2016. Let's just get on with it. First question is a pretty standard impulse and momentum question. Impulse is change in momentum, which we can quote as a formula like that. We're given the impulse it receives, that, so it's minus 4I plus 3J. We know the mass is 3. And we're being asked for the speed, so we need to first find the velocity. So the 3v minus 3 times by the initial velocity, which is given there. That's 3I plus 5J. Okay. Let's do a quick bit of manipulation there. We can see that this bit here is minus 9I, which when we take over we'll make it 5I, and this bit is minus 15J, which when we take over is plus 15J, which makes it 18J. Divide through by 3, we get 5 over 3I plus 6J. That's the velocity, but we want speed. Speed is magnitude of velocity, so that's the square root of the two components squared and added. And that comes to 6.23 meters per second. Right, so that's the first part done. Nice easy 5 marks, but often the marks do come easier in the earlier questions. The kinetic energy gained, because it's received an impulse, the velocity, obviously, the speed increases, and which increases the kinetic energy. Now, the kinetic energy gained, let's just label this. The kinetic energy gained will be equal to the KE, the final KE, take away the initial KE. So that will be, the final velocity is that, or the final speed is that, so the final kinetic energy is this. But we're taking away what the initial kinetic energy, which is this. Well, that's which is associated with this velocity, and we can just add the components there. So that velocity that speed squared will be, you just need to square the components there, and that, when we work it out, should come to 7.17. to 3 significant figures. Okay, so that's it. That's the first question done. Let's now look at the second question. This question is a power question. The first part is on a horizontal road. We've got a truck which is accelerating, and it's given both the acceleration and the speed at a particular instant, and it also gives us the power. So I'm not going to make a big effort to do a diagram, but even a very simple diagram I find sometimes helps us picture it. We've got a driving force here, we've got resistances, and it wants us to find the resistances. Now the forces aren't balanced here because there's an acceleration of 0.25, and it's that this particular instant the speed is 15 meters per second, and that's 0.25. is acceleration. So we've got a couple of formulas. P equals FV, power equals to force times velocity. We're given the power, which is 10 kilowatts, 10,000 watts, is equal to force times velocity, so that's F times by 15. So that gives me F equals to, I divide that through by 5, I get 2,000 over 3. Okay, so now I'm going to apply F equals ma, because I now have the driving force. And we've got the F in F equals ma obviously means resultant force, so the force pushing it forward, take away the resistance force, is equal to mass times acceleration. We are given the mass, which is 1,800, times by the acceleration, which is 0.25. So that gives me 2,000 over 3 minus R equals to 1,800 times by 0.25, that's 900 and half out 450. And that gives us a value of R equals to 217 newtons to 3 significant figures. Okay, so relatively straightforward first part of that question. Second part, also relatively standard I would say, is something going on in an inclined plane. Now, it's changed its power, which is not surprising, I suppose, because it's going to work harder to go up the hill. Obviously, well, it's a different F there, but I'm not really concerned. It's the driving force. It won't be the same driving force as before, but because it's a different part of the question, I'm not concerned at giving it the same label. And we also have a resistive force now, but they've changed the model here. It's of constant magnitude 30V, which to me, to be honest, more realistic, that the resistive force would be dependent, increase with the velocity. So that seems to kind of probably be a refined model, really. Going up with speed V, but this time it's balanced, so we've got A is equal to 0 because it's moving with constant speed. It says at some point constant speed V. Okay, and it gives us the new values. Don't forget the component of the weight. That's probably the bigger thing to consider here. We do know that angle sine theta, which is equal to 1 over 14 it's given us. So we can look at the forces balanced. Acceleration equals 0, so forces are balanced. So we resolve in parallel basically. We have F going upwards. That's the only force going upwards. Is going to be equal to the two forces going downwards. Now this one, the component is mg. Now the mass is 1,800 g. So it's 1,800 g sine theta. And this one here is already parallel to the slope, so that's plus 30V. Okay, but we can apply P equals FV again. Remember, that's all changed. P is equal to FV. The new power is 12,000 is equal to force times velocity. So we can sub in F, we can sub in the appropriate value for F, which is 1,200, 12,000 over V. So we have 12,000, that's right what we're doing, sub F, we have 12,000 over V equals to 1,800 G sine theta, but sine theta is 1 over 14. And plus 30V. Now at this point I'm going to do a bit of cancelling. I know we're going to have to use probably going to have to use a calculator anyway, but let's get back to the full screen there. Okay, so about that, I'm going to do a bit of cancelling. We've got the 0 gone off here, and let's just try and do without a calculator for the time being. So that equals to 180, let's call that 98 over 10 times 1 over 14 plus 3v. So now we've got a 10 cancelling again, factor of 10, and the factor of 14 cancels, divides exactly into 98 by 7, I think. Okay, and a bit fiddly, but I think it's going to work out. This is just tidy up 12550V, and that's going to come to 126 plus 3V. So then we have 1200 is equal to 126V plus 3V squared, and which gives us 3V squared plus 126V minus 1200 equals 0. Those all divide by 3, so that's V squared plus 42V minus 400 equals 0. And I think this is going to factorise. Obviously we can use a formula if we need to. If we have plus 50 and minus 8, I think that factorises. Okay, yeah, because minus, we're looking for two numbers that should multiply to 400, which is 8 and 5, with a difference of 42. So yeah, that's going to be right. Obviously this one's not appropriate, so we've got V equals 8 meters per second. Okay, so that's right, that's where we tend to nowadays. There we go. Okay, so that's question 2 done. Let's have a look at question 3. So question 3 is a work energy and power question with a connected particle. We've got a rough slope, and we've got this moving downwards here and this one going upwards. And it initially wants the potential energy lost, and then we're going to use the work energy principle in part B to work out what the speed is after it's moved a distance d. Right, well, I'm going to draw a quick diagram here just to look at what's going on. If we see this as what's happening initially, after it's moved down a bit, just maybe use a different colour. Like that. Then what's happened is that this has moved down a distance d, but this one has moved upwards, and we're given an angle here, sine theta. This has moved upwards by a distance d sine theta, which is 2 over 5d. So the potential energy lost will be equal to, obviously this one's gained in potential energy because it's gone upwards, and that's got a mass 2m. So P has actually gained in potential energy by half. Remember the formula is half mv squared, by half times 2m. No, we're not using its potential energy, which is mgh. Apologies. So that's 2m g times by the height that it's gained, which is d sine theta. Well, that's right, actually, right in the, we've worked out there, d times 2 over 5. Right, so that's a gain in potential energy, but this one's lost because it's gone downwards. It's got mass 3m, so using mgh, that's minus 3m g d. So that equals to 4mg d over 5 minus 3mg d, which is equal to minus 11 mg d over 5, which means that 11 over 5 mgd loss of kinetic energy because of the negative sign. Okay, so that's part A. Part B, I tend to, with these more involved questions, people seem to have their own different ways of doing this, but I always think it's a nice formula to actually work on here. Is work done by external force is equal to the change in mechanical energy. In other words, the kinetic energy plus the change in kinetic energy plus the change in potential energy. Now, if there is no external force, friction or driving force, whatever, then obviously if K goes up, P goes down. Now, having marked this in the past, often students forget about the external force. And so we've got to be careful. So yes, there'll be an increase in one and a decrease in another, but overall we've got friction on here that's going to take from the system completely. So we've got the gain in potential energy is half times by, let's just 3m times v squared, that's the particle Q, plus a half times 2m v squared, that's the particle P, that's the total potential energy. This energy is lost, so that's minus 11 mgd, kinetic energy is decreased, hence the negative sign, is equal to the work done by the external force. Now the work done is equal to, we are given a frictional force, 3/5 mg. So it's going to be 3 over 5 mg times by the distance d, but it's a negative because friction is going to reduce the overall mechanical energy in the system. So we've got a negative sign there. Okay, so I'm going to do a bit of cancelling again. So m cancels. Okay, and let's just see if we can get to an answer here. Oh dear, that's happened too many times. Never mind. Okay, right. Okay, so let's just take everything over to the other side. These two together here, that's 3 over 2 plus, that's 5 over 2 v squared is equal to 11d, oh, I've forgotten the 5 there, that'll be the same, 11 gd minus 3 over 5 gd. So that gives me, if I cross multiply, v squared, 11 minus 3 is 8, but I'm going to times that by 2, so that's 16. And then divide by 5, I'm going to have 16 over 25 gd, which is our answer for part B. Now onwards to part C. Right, okay, so for part C, we've got a bit unusual. It says it's given us the D is 1.5, which means that we can work out, use this formula to work out V. So let's do that. V is equal to the square root of, well, this bit square rooted is 4 over 5. So that's 4 over 5, the square root of G times D, 1.5 G. And that equals to, well, I've got an exact answer of 14, the square root of 30 over 25. I'm going to store on my calculator. It's 3.067, a lot of stuff there. But the thing to note here is it is accelerating. We don't need to work out the acceleration. It is acceptable to work it out, but it says it's released from rest. So that must mean that u equals 0. So we can use S is equal to u plus v over 2 times t to work out the time taken. Okay, so that gives us S, which is 1.5, is equal to u plus v, so that's 0, u is 0, so that's 3.067, and all the other stuff divided by 2, times by t, and that gives us a value of t equals to 0.978. Oh, let's use big T because I've used big T in the question. That's the particular value of T when it's gone to 1.5. So 0.978. Okay, so that is the third question. Now let's look at the fourth question. Well, surely this first part's relatively straightforward bit here. We've got a uniform lamina and we've got a rectangle and a triangle, so we've got a composite shape. Let's work out the ratio of the masses. I often like to, with these questions, work out the ratio of the masses, cancel that ratio down, and then put into an equation just to make it look a little bit neater. So we've got the rectangle here, A, B, D, E. So it looks like a trapezium there, but there again, rectangle A, B, D, E. That's got area 6a times 3a, so that's 18a squared. Then we've got the triangle, which is BCD. That's got area half times 6a times 3a squared. It's basically half of that, 9a squared. And then we've got the composite shape, which is the total of those two, is 27a squared. Now, cancelling that down, we can just divide by 9a squared each one. So that comes to 2, 1, and 3. So that's the ratio. So I think that's going to be useful for the ratio of masses. That's the ratio of masses. But the distances from AE, so just working from here in this direction, of centre of mass. Well, this one's at 3a over 2. This one here, well, this is a triangle here, and we know that it always goes a third along the way here, so that's A, but it's already 3a there, so that's 4a. Okay, and then this distance is the one we want to find out. So we do need to write our equation down. It's that times that plus that times that plus that times that. Sigma mixi is equal to x bar sigma mi. So that's 2 times 3a over 2 plus 1 times 4a is equal to 3x bar. That's going to make that x bar is equal to 7a over 3. Okay, so nice easy 5 marks there. It's not going to get much easier than that for a centres of mass question. However, they make up for a little bit in part B with a bit of kind of moments and things where we're really mixing up a bit. It says the lamina is freely suspended from A here, and a horizontal force of magnitude F newtons is applied to the lamina at D. Now, the centre of mass, as we know, is going to be there, say, where that distance is. That distance there is 7a over 3. Let's mark it in red. Okay, and we're also told the mass of it now, I think 4g. So mass is 4, so the weight is 4g. Now, obviously, if there was no force there, it would tend to tilt this way. So we need to have a force a horizontal force tilting in the opposite sense. There. Let's call it force F. Right, now obviously this whole thing is going to be in equilibrium, so wherever the force is, we can think of it as some kind of hinge, or it could be a tension. It doesn't matter really what it is. We're going to have obviously a vertical bit, let's call that Y, and a horizontal bit to balance out the F here. Okay, now it's not going to be too hard to find what Y is. Y is going to equal to 4G because it's got to be balanced horizontally, and X is going to be equal to F because it's going to be, sorry, horizontally, vertically. Apologies for getting things the wrong way around. And X is equal to F, which is the horizontal bit there. Right, so we know that Y is 4G, so in order to work out F, we've got to take moments. So if we take moments about A, that should work out pretty nicely. So moments about A, well, F, let's just consider this force first. The perpendicular distance there is 6A. So that's F times 6A. And that equals 4G, this force here, times by the 7 at the perpendicular distance, which is 7A over 3. So that's 4G times 7A over 3. Now the A cancels, so we're going to have F equals, that's 28 over 3, but 28 is going to cancel that, so that's going to be 14G over 3. No, over 9. There'll be a 3 there, which would make it 9 underneath. Okay, so that's F. Now, going back to this, it wants the magnitude of the force, the overall force exerted on the lamina. Let's call it F. It's going to be coming up here like that. But we now know that X is also equal to, because it's equal to F, we know that X is equal to 14G over 9. So that means that the overall force F, using Pythagoras' theorem, is the square root of x squared plus y squared, which is equal to the square root of 4G squared plus 14G over 9 squared. And if I work that out, I get 42.1 newtons or 40 newtons to two or three significant figures. Okay, so that's question 4. Now let's have a look at question 5. So here we have our statics question. We've kind of already had a statics question with the lamina thing here, but here is our uniform rod. It's kind of, we're going to come somewhere. We've got a tension, it says, we've got a uniform rod, so the weight is going to be in the middle of that rod, and the weight is 6G. I'm going to just get the diagram sorted first. It's a light, inextensible string, so we're going to have a tension there. It actually, we kind of expect it to be hinged, but it talks about friction a lot on the wall. So we're going to split the force into a frictional force there and a normal contact force there. Okay, now let's mark some angles on, because I think it's kind of essential that we get the angles right here, because we've got these two angles here, and I'm guessing that the biggest mistakes that are going to happen here are to do with confusion with moments equations and resolving equations and getting the angles wrong. That's 70 by a corresponding angle with this here. So we can write that sending. Now, although I've got the 30 degrees here, which will be useful for my moments equation, it will be less useful for my, well, it won't be useful at all for my resolving vertically and horizontally equation. Now, we know that the whole of this is 70 because it's alternate with the 70 here. So this angle here is going to be 40. Okay, so I think we've done enough to get started now. Okay, so it talks about the tension in the string. It's often a good, if you've got a hinge or a frictional point, it's often a good time to take moments about that. And in this case, we've only got the two forces to consider, the tension and the weight. So it should come out quite straightforwardly. If we take moments about A, right, now the way this works is, the way I often think of this is, just look at the perpendicular components are the ones that are going to matter. It doesn't look perpendicular, does it? Never mind. I'll try and draw it a bit better and picture it. The perpendicular is going to be more like that, isn't it? And that perpendicular component is 6g sine 70, because it's away from the marked angle here. Whereas this perpendicular component here for the t is t sine 40. That's not right, is it? It's t sine 30. I did say that it's more likely to. We've got the. Yeah, maybe in some ways, I might put that in later, it's sometimes a bit distracting seeing it afterwards. Yeah, so we want that force there. So that's t sine 30. Okay, so that's t sine 30 there. And of course, the bits going along that way don't matter because they have no turning effect about A. Oh, sorry, I've got that in the wrong direction, but it doesn't matter because it doesn't have a turning effect anyway, but you get the gist. So the moments equation is t, this is the anti-clockwise bit, sine 30 times 2. Don't forget to times by the distance. So often students forget to times by the distance, which is penalised quite heavily. And plus 60 is equal to 60, this force, sine 70, times by 1. I still put the 1 there to just make it dimension, to have the dimensions of force times a distance, to make it clear it's a moments equation. Right, now sine 30 is equal to 1/2 times 2, so that just gives us t is equal to 6g sine 70. Okay, now if we work that out, that's going to come to 55.3 newtons to 3 significant figures. I've got a more precise answer stored on my calculator, or we can use 6g sine 70 for future bits. So that's not too bad for 4 marks. That's part A. Part B, now with these questions, I mean, 3 equations is normally what we want, and it's more often than not 2 resolving equations and 1 moments equations is going to be the best way to go. Not always, but normally 2 resolving equations and 1 moments equation. People often take 2 moments equations, and sometimes it can be harder, but it's not hard and fast rule, but often in these cases that's the way it's going to be. I'm going to mark that angle in again now. It did distract us a bit before, so it just shows you, or distracted me anyway, when I was doing the moments equation. That angle's 40 degrees. To get my resolving horizontally, I've got my R force going that way and my component of T going that way. Now that's now going to be, because it's this angle that's of interest, because that's the angle with the vertical. So with the horizontal, the component is T sine 40, and with the vertical, the component is T cos 40. So I can, because if I resolve horizontally, I get R equals T sine 40. but I know what t is. That's 6g sine 70. So r is 6g sine 40 sine 70. So resolving vertically, I've got the mu r going up. I've also got the component of the tension going up, plus t cos 40. And I've got the 6g going down, so that equals to 6g. Okay, so that enables me to basically work out what mu is. I haven't even mentioned where we're going. It's so often we get to the point where we're just going through the motions. You know that you're going to have to work something out, and often it's going to be resolving equations. Occasionally end up doing one more equation you need to, but it's often a good habit to get into, just writing your equations down. So got mu r plus t cos 40 is equal to 6g. Now, right, so it's mu times r, which is that. 6g sine 40 sine 70 plus t, which is that 6g sine 70 cos 40, instead of this bit subbing into that bit there, equals 6g. So if I take that over and work out mu, that gives me mu, taking this over to that side, so that's 6g minus 6g. Tell you what, I'll cancel before I do that. It doesn't matter really, but I know we're going to work out, use a calculator anyway, but if there's some obvious cancelling, I always say take that chance, don't just, no, not a chance, just do that. So 1 minus sine 70 cos 40. That's that taken over to the side, divided by sine 40 sine 70. Okay, that's 0.464. Okay, I've got that number also stored in the calculator more precisely because we're going to need it in the next part. Okay, so right, okay, so the next part, just got a little diagram here, might help. We want the direction of the force going up here. So that's the direction of this force here. I'm going to give it with the wall, with the vertical, so this angle alpha here. So we have an r this way and a mu r here. So we can say, using SOHCAHTOA, opposite over adjacent, tan alpha is equal to opposite, which is the r, that's that bit, divided by hypotenuse, which is the mu r, which is that bit. Now mu is equal to that. I've got it stored more precisely in the calculator. That's 1 over mu. So alpha is equal to arc tan 1 over mu. And that comes to 65.1 degrees. And don't forget to say that whether it's to the vertical or the horizontal, and this time it's to the vertical. Okay, so that's question 5. Let's look at question 6. Okay, so question 6 is a projectiles question with what this is sometimes called the equation of path question. You might have seen questions where it does this more generally, where you have a sec squared in it, and tan x and that type of thing. But this has got some numbers in, so we'll work with those. The initial velocity is 7 that way, and 7 square root of 3 going that way. It's going to go up that, but so that's what it is initially. So let's just go horizontally first. The horizontal distance x is going to be equal to 7t, because that's just using the fact that there's no acceleration horizontally. Distance is equal to speed times time. Okay, now vertically, we've got the initial speed of u equals to 7 over the square root of 3. We want to work out an equation for y, and we've obviously got a is equal to minus g, and t we'll put in there as well. We're going to use s equals ut plus half at squared. So we have y equals u, that's a 7 over the square root of 3, t, minus a half g t squared. Well, from here, let's go back to here for a second, we've got t is equal to x over 7. So we're going to sub t equals x over 7 into there. So we have y equals 7 over the square root of 3 x over 7 minus a half g x over 7 squared. Now really it's done now. I mean, we can see that the 7 cancels, but we've done enough really. Yes, this happened again. Happens too often, that. Okay. We can see that the 7 cancels, and we're going to end up with what we've been asked to show. So that's y equals the square root of 3x minus g over 98 x squared as required. Or QED or so, or nothing actually. It's just quite nice to close it off in some way. Okay. Part B, find the direction of motion. Now I quite like this question because it's actually the standard way of doing this. Remember, it's direction of motion, it's nothing to do with displacement here. So really what we want to do is use the fact that it's always going to be 7 going there, and we could use v is equal to u plus at to work out the vertical motion. It actually ends up going downwards there, and you know that t will be equal to 20 over 7 because x is, and you can use that in there and it'll work out. Go do that, which is fine. It's the most standard way of doing it. But because we've got this equation here, I'm going to do it slightly differently. I'm going to differentiate and get the gradient of it, and because basically that gives us the path of the parabola, and we want the direction at a particular time. So if we differentiate, we get dy by dx is equal to the square root of 3 minus g over 49 x squared. Right, now that, and it wants us to work out, it's when x is equal to 20, so we can put 20 in. So when x equals 20, we have dy by dx equals the square root of 3. Let's work this out. 9.8 over 49 times 20 squared. Oh, it's not 20, of course. This is 20 squared. But it's not 20 squared. I haven't differentiated properly. It's silly. I've times 20. I knew something wasn't right. So differentiate is g over 49x. Oh dear. So that works out, because that 9.8 over 49 works out 5. So that's square root of 3 minus 4. Now, I note that that's negative. So it's actually given us a gradient, a negative gradient. So for every, it's basically on its downward path somewhere. So for every one across, it's going minus, or to go in square root of 3 minus 4. downwards like that. But once we've got a gradient, we can actually easily work out the angle, because that angle alpha will just be the arctan of the gradient. So alpha is equal to arctan of square root of 3 minus 4. So that's arctan that comes to minus 66.2 degrees. So we need to make we need to close that off by saying 66.2 degrees to horizontal. Just find it's quite a nice way of doing that one, rather than just the standard way of applying v is equal to u plus at and then working out things with the numbers. It doesn't really matter, to be honest. Anyway, there you go. Then part C. Now part C is about, it's going back to talk about displacement. Okay, now it says displacement at the times it's actually gets such it's gone twice as far, its x value is twice as far as its y value. Well, remember that the x displacement is going to be equal to 7t. Okay, now that's going to be double whatever the y displacement is because of this ratio here. Now, for the y displacement we can work out just by using s equals ut plus half at squared. Basically putting this formula back in, and we've already worked that out anyway, so that's 7 the square root of 3t minus a half gt squared. Right, now certain things are going to happen here. T will cancel part of it, t, and t. Okay, so we'll get 7 is equal to 14 the square root of 3 minus 4.9 t. So t equals to 14 the square root of 3 minus 7 over 4.9. Right, there's a mistake there. Let's leave the g there because it's 2 times the half there, so it's equal to, that's the exact answer, g, and that works out to be 1.76 seconds. Okay, so that's using the fact that it's gone the x value and the y value in the ratio are 2 to 1. So if we double the y value, the y displacement, we get the x displacement, and using that, so hence the 2 there. Okay, so there we go, that's the question 6. So one more question to go. Let's have a look at that. So this is a collisions question with coefficient of restitution. We're told that two particles are moving in the same direction, particles A and B. A and B. So they're going with speeds, A is going with speed 3 meters per second. And B is going with speed 2 meters per second. We've got masses of these two, m and 2m. And then afterwards, so that's before, after, we've got them going, and they've given us the labels for them with speed v and w. And we're also told that these are all unchanged, so we shouldn't really slip up here. It's quite nice for a part late in the paper. There's nothing really too nasty here. We're going to apply conservation of linear momentum. So we have 3 times m plus 2m times 2, that's for the momentum before, is equal to momentum after, so that's mv plus 2mw. Now m cancels, okay, and we end up, that's 3 plus 4, that's 7, is equal to v plus w plus 2w. So that's our conservation of linear momentum equation. Now, then we've got Newton's experimental law, or Newton's law of restitution. Here we're told speed of separation is equal over speed of approach is equal to the coefficient of restitution, which is giving us 2/3. Now, the speed of separation, W is going to be going away. B is going to going away from A with relative speed W minus V. Obviously, 3 is going towards A is going towards B, with 3 minus 2, and that equals to 2/3. So we have W minus V equals 2/3. So we just have to solve this equation to get W. If we add the two, I'm not going to bother getting rid of the fraction because it's pretty easy with the V and the V here. So adding the two, we're going to get 3W, that plus that, and the V is going to cancel, is equal to 7 plus 2/3. And that gives me W is equal to 23 over 9 as required. Okay, and then that's part 1. A1. And then part 2, we can now easily just put the 23 over 9 back into either of these two, say. So let's put it back into this one. We have V is equal to 7 minus 23 over 9, 2 times 23 over 9, so that's 46 over 9, 63, minus 46, which is 17 over 9 meters per second. Okay, so that's the first part. So that's quite nice, 7 marks for this late in the paper, but we make up for it again a bit. We'll put the next part of the question. I think I've seen something like this before. They talking about at the point where these have collided, what's going to happen is that B then hits a wall. So B is going to come back, and we're told the wall is 3 meters away. And let's say they collide there. Let's say that's the motion of B, and they're 3 meters away. Okay, that's B. Now A, in the same time, is going to just go this distance here. So if we call that distance D, this is 3 minus D. Now they've both done this in the same time. So B has gone all the way to the wall and back again. In the same time, A has actually gone not as far to the wall, 3 minus D, and then they've collided. So second collision. Now we can use this to set up an equation because it's done in the same time taken. Let's consider the easy one for the first, which is A. The time taken is going to be equal to the distance divided by the speed. And A doesn't change. So we've got the speed of A, which is V, is V 3 minus D, 17 over 9. Okay, but B does change its speed. Now this is important because during this part of the thing, it's going with speed 23 over 9. But we're told that we've got the coefficient of restitution of this with the wall is half, so it's going to rebound with speed 23/18. So it changes its speed. Okay, so let's split. So we need to split into 2 bits. We can't just add the 2 distances and divide by 1 speed. We've got the first bit before it collides. It's gone 3 meters at a speed of 23/9. That's the bit before it hits the wall. Now after the rebound, it does this extra bit, and that is gone for d over, now the speed has changed, 23/18. Okay, now I'm going to get rid of the stack fraction, so we've got a nice equation here. Well, nice, a relative term I suppose. Let's just kind of get rid of the stack fraction. 9, 3 minus d over 17 is equal to 9 times 3 over 23 plus 18d over 23. I'm going to cancel again. Now, some of you might bother cancelling, but I find I'm more likely to make a mistake on the calculator than I am with my cancelling. So anyway, so there we go, that cancels. Now, so we've got 3 and 2 here. Now let's cross multiply. So we have 23 times 3 minus d is equal to 17 times 3 plus 2d. So 23 times 3, that's 69, minus 23d is equal to 51 plus 34d. So that gives me 34 plus 23, that's 57d is equal to 18. So d equals to 18 divided by 57, which is 6/19, which is the final bit of this paper. So that's it. I hope you found the video useful. Sorry for this few technical glitches and the odd slip here and there. I think we got there in the end, and as I say, I hope it was worthwhile. Thanks, bye.